Hello world, we are the Gapplebees. I'm Karloot,
I'm James.
And I'm Grace.
and today we will be talking about aluminum, titanium, and titanium aluminide, and their metal properties.
To start, we will discuss a general stress-strain curve and how to find certain elements used in material science such as Young's modulus, yield point and strength, tensile strength, ductility, resilience, and toughness. To find the elastic modulus, also known as Young's modulus, find the slope of the elastic region, which is the linear portion of the graph. To find yield strength, in engineering practice, we draw a line parallel to the elastic region on the stress-strain curve that goes through 0.2% strain. The intersection between this parallel line and the curve is the turning point between the elastic and plastic region, known as the yield point, which we can find at point B. The stress associated with this point is known as the yield strength. To find the tensile strength or ultimate strength, which is the maximum stress that a material can endure, we find the highest point on the curve. On our graph, this would be point D.
How do you find ductility? Ductility is basically percent elongation and percent reduction in area. To find these, we use a formula in combination with measurements before and after testing. To find percent elongation, we do the final length of the specimen minus the original length of the specimen divided by original length times 100. Percent reduction in area is original cross-sectional area minus the final cross-sectional area divided by the original times 100. How do you find the resilience? Resilience is the ability of a material to store energy before yielding. We can find this by taking the area under the curve between zero strain and strain when the material yields. To do this, we could treat the elastic region as linear and use the formula for the area of a triangle. Therefore, resilience equals yield strength times yield strain divided by 2. On our graph, this would be the green section. How do you find the toughness? Toughness is the energy needed for the material to break. One way to find this is to take the area under the whole stress strain curve, which is the blue section of our graph plus the green section.
Our first metal is aluminum, which is excellent at allowing electricity to flow through itself and equally as reliable with holding thermal energy. For this reason, aluminum is popular amongst electrical companies and their capacitors, wiring, and even antennae because of its lightweight and economical benefits. It is also used in cooking utensils like pots and pans because of this conductivity. Aluminum is used for vehicular parts within the engine and transmission components, more wiring, and even parts of the frame itself. Aluminum has also proven capable at softening rough terrain by being extremely shock and even sound absorbent. Our military even uses the metal, as it has been used in multiple tools and weaponry like artillery, torpedoes, missiles, and chaff or flares. As you all heard a few slides back, Young's modulus is the slope of the elastic portion of the graph. Aluminum has an elastic modulus of 6.9 times 10 to the 10th power, or about 69 billion pascals, which is used as a constant in certain calculations. Now, aluminum has a yield strength of about 95 MPa, or about 95 million pascals. This means that at this amount of stress, the piece being tested will begin to differ from elastic properties to more plastic ones, resulting in deformations beyond repair. Finally, a tensile strength of 225 megapascals is the maximum amount of stress that the sample can withstand. This is the highest point on the graph.
Next metal, titanium, the 22nd element in the periodic table, is celebrated for its exceptional corrosion resistance. When exposed to air and water, it forms a thin protective oxide layer that prevents further oxidation, making it ideal for harsh environments in marine and chemical industries. With a high strength to weight ratio, titanium is both incredibly strong and lightweight, making it perfect for critical components like gears, sprockets, and ball bearings. Its melting point ranging from 1650 to 1670 degrees allows it to withstand extreme temperatures and stresses, particularly in aerospace applications. In orthopedics, titanium is used for implants such as bone plates, screws, and joint replacements. Its strength and ability to integrate with bone promote effective healing and long-term support for injuries. The strength curve for titanium demonstrates high stiffness with a Young's modulus of 1.16 times 10 to the 9 pascals. It has a substantial yield strength of 560 megapascals and good tensile strength at 650 megapascals. Titanium exhibits elastic behavior up to the yield strength, followed by plastic deformation and strain hardening until it reaches the ultimate tensile strength. Beyond this, it can fail due to necking and fracture.
Now for our metal alloy, titanium aluminide. This new and upcoming metal combination is known for being extremely light, as well as its qualities to oppose rust, corrosion, and oxidation when opposed to the elements. For this reason, the alloy has been used in aerospace and aeronautical applications and automobiles. Titanium aluminide's resistance to heat has caught General Electric's attention, and they have decided to use the metal in their current Gen X engines and even the future GE 9X jet engine. With observed retention of its properties leading up to its melting point of 1600 degrees Celsius, why this alloy has caught the eyes of major engineering companies should be no surprise. This is the third time we're going over this, so I'll make it brief. With an elastic modulus of a whopping 176 billion pascals, this alloy is not messing around. An average yield strength of 400 megapascals and an ultimate tensile strength of 450 MPa means that it's going to take much more than a firm grip to break titanium aluminide.
What we'll do is analyze a real-world application of what we've discussed today. We're going to dive into a problem involving tensile forces and look at how two different materials, aluminum and titanium, react to the same load. This problem is framed around how the change in length and width of two cylindrical metal specimens is calculated when pulled by a 4 kN force. The problem states that we have two cylindrical specimens made of metal 1 and metal 2, specifically aluminum and titanium. Each specimen has a diameter of 20 centimeters and a length of 1 meter. Both are pulled under tension with a force of 4 kilonewtons or 4,000 newtons. The question asks us to determine the change in length and width of these specimens under the force. Before we solve it, let's go over some key symbols and variables which we can find in the top left corner of our slide. Sigma represents stress, epsilon represents strain, delta represents change in length, F sub t represents force, E is Young's modulus, A sub 0 is the original cross-sectional area, L sub 0 is the original length, W sub 0 is the original width, and nu is Poisson's ratio, which is a constant for the material, often assumed to be 0.33 for metals like aluminum and titanium. Now let's start with the aluminum specimen. The key formula we'll use here is stress equals force divided by original cross-sectional area, which equals Young's modulus multiplied by strain. By rearranging this formula, we can get strain equals force divided by original cross-sectional area times Young's modulus. Next, if we look at the change in length specifically, we can use the relationship between deformation, strain, and original length and rearrange to get deformation equals original length times strain. If we substitute the formula for strain that we found earlier into this equation, we find that deformation equals the original length times force divided by original cross-sectional area times Young's modulus. We know that the original length of the specimen is 1 meter and the force applied is 4,000 newtons. Now, given the diameter of the specimen is 0.2 meters, we can use this to determine the original cross-sectional area. We know that the radius is 0.1 meters, so the original area would be pi times 0.1 squared. And as we learned earlier, Young's modulus for aluminum is 6.9 times 10 to the 10th power. If we substitute these numbers into the equation that we derived, we find that deformation of our specimen, which equals the change in length for aluminum, is approximately equal to 1.845 times 10 to the negative 6 meters. Okay, now that we have change in length, let's move on to calculate how the width of our specimen changes under the tension. To do that, we'll use formulas under the change in width section. We have a formula for lateral strain, which is equal to the negative of Poisson's ratio multiplied by strain, and we have a formula for lateral deformation equal to original width times lateral strain. If we combine these formulas, we arrive at a formula for lateral deformation equal to the negative of original width times Poisson's ratio times force divided by original cross-sectional area times Young's modulus. If we substitute our values into this equation, we find that the change in width of our aluminum specimen is approximately negative 1.218 times 10 to the negative 7 meters. Now let's move on to our titanium specimen. We've already derived the formulas for change in length and width, so the only thing that we need to do differently for this sample is use Young's modulus for titanium everywhere that we use Young's modulus for aluminum in our previous sample. So if we look at change in length for our titanium sample using 1.16 times 10 to the 11th as Young's modulus for titanium, we can get change in length to be 1.098 times 10 to the negative 6 meters. And change in width, again, following the same procedure as we did for aluminum, but with our new Young's modulus, we get that change in width of our titanium specimen is approximately negative 7.244 times 10 to the negative 8 meters. The differences in behavior stem from the material's Young's moduli. Titanium is stiffer, meaning it stretches less under the same load. And that wraps up this problem. Thank you for watching and have a great day.